We now delve into the world of motor control, which motor, which controller. And we start right away with part one, which is a triple session with EBV Electronic. And the first lecture is on the topic of choosing the right motor. Our first speaker will be Canberg Césaire, Digital Motor Control Software Field Application Engineer at EBV Electronic. Canberg has been working at EBV Electronic for more than 2 years. He completed the Electrical Machines and Power Electronics Master's Program after earning a degree in electrical engineering. He worked as an embedded software developer and worked on power electronic systems control in many projects. He has expertise in motor control and power systems control. The right man in the right place. And in his second lecture, which he will give directly after the first, he will explain us why choosing PSOC control C3M for multi-BLDC-motor control.
Hello everyone and welcome to our webinar. My name is Canberg and I am motor control specialist at EBV Electronic. Today we will be together in two different sessions. I would like to start with the topic of selecting the right motor. And if we take a look at our agenda for motor selection, we need to understand why this choice is critical and look at the selection criteria. Then we will look at the schematic of the classification of motors. Under overview of motor types, we will talk about the general operating principles and advantages and disadvantages of 4 different types of motors. Afterwards, we will take a look at the table where we match motors with application types. And we will conclude by reviewing the motor control algorithms offered by Infineon. And the main question is why motor selection matters. This issue actually directly affects the quality of our design. With a wrong motor selection, even if the desired performance level is achieved, efficiency may be low. And the other term determines control complexity. With the right selection of the motors, it is not necessary to produce out-of-the-box solutions to achieve the requirements of the control. This allows for simplicity in control. And the last one directly affects system cost and reliability. Of course, at the end of the day, all these details come together in cost and system reliability and have a direct impact on the result of the project. And when we look at the key criteria in motor selection, these bullet points come from the interaction of motor selection with other components of the system, like as the application type related with the other bullet point torque and speed requirements, and position accuracy needs directly related with the motor selection. And this selection is both input and output inverter design, mechanical design, and software development affecting. And when we look at the motor classification, it is possible to make the categorization seen here in different ways. However, in this accepted structure, the main classification depends on the power source, AC, DC. Construction and the resulting electrical differences then create new categories. Here we have 3 different main categories, not just the AC and DC, with special purpose. These categories also have different type of motors within them. It is also easier to understand purpose-built motors if they are considered as a special category instead of being grouped under other main categories. This is because although these motors are structurally similar to those into the other group, they have slightly different driving methods and thus very different operating principles. And nowadays, BLDC and PMSM motors projects are continuously increasing. Therefore, these two motors are considered to be very similar. While this is acceptable, it can be seen from this classification on the screen that these two motors actually have different structures in different categories, like as AC and DC. We can say that the most important difference is in the back EMF waveform. And let's take a look at the operating principle of the 4 different motors that come from this classification. The first one is the induction motors. The electric motor, which runs asynchronous speed, is known as induction motor. And an alternate name of these motors is the asynchronous motor. Induction motor mainly uses electromagnetic induction for changing the energy from electric to mechanical. Based on the rotor construction, these motors are classified into 2 types, namely squirrel cage and slip ring. It is more useful to understand the working method through the graphic on the screen. If we examine the graph, the synchronous speed corresponds to the rotating speed of the stator magnetic field. At synchronous speed, no torque is produced by the motor because no current is induced in the rotor windings. If the rotor rotates at a lower speed than the stator field, the motor runs in the motoring mode. Otherwise, the motor operates in a generator mode. The maximum torque, which can be obtained at the motor shaft, is called pull-out torque. The nominal torque is conventionally half of the pull-out torque. The motor usually operates in the linear region between the positive and the negative nominal torque, which is marked by the green line. And the second one, our second motor, is the PMSM. All name is permanent magnet synchronous machine. That means we can talk about general synchronous machine principles with special differences. Synchronous machines can provide torque when a rotating electromagnetic field and a constant field are standing still relative to each other. To develop a constant torque in a synchronous machine, the stator field must rotate synchronously with the rotor because the excitation fields are fixed to the rotor. The field excitation magnets are mounted to the rotor of the synchronous machine. And I need a marker. Yes, here. The, the D-axis refers to the direct axis. That means main flag path axis of a synchronous machine, while the Q-axis refers to the quadrate axis. The load angle describes the angle between the rotor and the stator fields. The graph in here, just wait, okay. The graph in here shows the sinusoidal dependency of torque on the load angle, theta. This relationship is only valid when all voltages remain constant. The magnitude of the pull-out torque, that means maximum torque, if you remember from the other machine, from the induction one, the pull-out torque can only be varied by changing the excitation current. If the excitation current is constant, like as our case in the PMSMs, then the load torque will determine the load angle theta. If the two fields are perpendicular, like as a 90 degrees, the highest torque is produced. That is the key case. If the two fields are aligned, no torque is produced. To operate a synchronous machine at different torque speed points, it is necessary to adjust voltage or current at frequency. Modern drives with PMSM are mostly fed by frequency converters to generate a three-phase systems with variable frequency and voltage or current. Consequently, it is possible to control the speed and torque. And the third one is the brushed DC motors. Here we have a summary of the strengths and the weakness of brushed DC motors. One of their biggest advantages is simplicity. They are very easy to control and they don't require complex electronics or powerful microcontrollers. That makes them a cost-effective option for basic applications. However, there are also several drawbacks. As you can see from the image on the right here, uh, these motors rely on brushes and a mechanical commutator. Over time, this brush wear out and need replacements, which increases maintenance and reduces the motor's lifespan. The mechanical commutation also causes sparking, which can lead to electromagnetic interference, a concern in sensitive electronic environments. Additionally, since the brush can get damaged by dust or particles, these motors are mostly used in clean environments to avoid issues like clogging or commutation failure. So while they are simple and easy to use, rush DC motors come with significant trade-offs in terms of durability and reliability. And these slides give a quick overview of how BLDC motors work and why they are widely used. On the top right, we see the internal structure of a BLDC motor. The rotor is made of permanent magnets, and the stator has windings. Unlike brushed motors, there are no brushes here. It's good for us. Instead, electric commutation is used. The Hall sensors shown on the stator detect the position of the rotor and help the controller switch the current in the correct sequence. At the bottom, we see two common driver circuits. Left one for a single-phase BLDC and the other one for a three-phase BLDC. Both use MOSFETs to energize the motor windings based on sensor feedbacks or sensorless control method coming from the observers. Because of this brushless and sensor-based or sensorless design-based, BLDC motors offer many advantages, such as high efficiency, low maintenance, because without brush, and longer lifespan and high reliability, as listed on the screen. And in this table, we can see the application areas of these motors and the advantages of these motors in these areas. Like as for PLDC, we can think about where suitable, speed control and efficiency come to the front. For PMSM, it is especially ideal for household appliances and vehicles that require precise and quiet operation. For the other category, the induction motors, it is preferred for its industrial robustness and simple structure. And the last one, the brush DC, useful in low-budget projects that do not require complex control, like as a toy. And the next one, we can see the very big table from the Infineon side. In this table, we see the 4 different algorithms that Infineon supports for motor control. A quick look shows that RFO, rotor frame orientation, and SFO, stator frame orientation, are simple and specific version of FOC, field-oriented control, used for a specific purpose. By choosing RFO for position and speed control without sensors, we can realize an efficient and non-complex design. With similar logic, if we make a choice for torque control, we can choose SFO, stator frame orientation. I think there is no need to talk about the details of FOC nowadays, Anyone who Googles the topic of motor control comes across this control method first. The other method, the most classical and still very common one, is the trapezoidal control. In designs with this method, the control system is quite simple and therefore it is easy to tune the system. It is a fast and easy way to create good solutions for the motor control. And what is the next? We talk about different type of motors and how do we control these motors efficiently. Of course, we need a microcontroller and we have the PSOC control C3. And the second question will occur, how do microcontrollers support complex control techniques? We need to talk about too much details to control the motors, like as from the Infineon side, controllers, filters, observers, system, subtitles. And we have the another detailed blocks under that subtitles. For that reason, let's explore the use of the PSOC control C3 in motor control applications in the second session of this webinar. And in this session, we will examine the application areas with PSOC control C3 and take a look at the general structure of this new MCU. Then we will cover analog and timer structures, which are important for motor control. At the end, we will examine the benefits of PSOC control C3 for motor control application. As you can see on the screen, Infineon has released an MCU suitable for all industrial applications. As the name suggests, the PSOC control C3 is specifically designed for power control and motor control applications. That's why Infineon put the word control in its name. When we look at the motor control focused applications on the screen, we can easily address the points robotics, air conditioners, power tools, home appliance, industrial automation, and light electric vehicles. Too much options. And another important point is the use of next generation switches in motor control applications, driven by advancing technology. There are specific requirements for silicon carbide, called SiC, and gallium nitride, called GaN, and the PSOC control C3 is capable of meeting those needs. The PSOC control C3 comes in 3 different lines. The entry and the main lines have already been released, while the performance lines hasn't been released yet. However, it will soon join the product family. From a motor control perspective, we can see that the entry line is sufficient for applications using basic drive techniques. When the drive method becomes more complex, the main line becomes the more suitable option. Although the performance line is targeted for high precision and computation heavy applications like servo drives, it is still possible to address these needs with the main line as well. A common type where both motor control and power conversion are handled by the same microcontroller, like as home appliance projects, the main line offers sufficient performance. And if we take a look at the block diagram of this product, we can see that it's an microcontroller based on the Cortex M33. In addition, it features DSP and FPU units, DSP digital signal processing and FPU fixed point unit, float point unit, sorry, and which enhance performance for motor control applications. And of course, Cortex is a must-have, and it's included as well. I will talk in detail about the 12-bit SAR ADC shortly. Another important block in the analog architecture is the internal comparators, which can be easily used to evaluate the feedback signals needed for motor control. Additionally, in scenarios designed to protect the system, such as overcurrent protection, the necessary reference signals for these comparators can be easily generated using the internal DUC peripherals, digital analog converter peripherals. I will also cover another critical topic, which is timers for motor control shortly, and with the trigger mark system, which enables effective coordination between the like as ADC and the timer blocks, interactions, and between peripherals can happen in less than 1 nanosecond, allowing the system to operate automatically without needing CPU power. This microcontroller has a PSA Level 2 certification, reflecting the growing importance of safety. It is also SEAL 2 compliant for functional safety and provides Class B support as well. Let's take a closer look at the details of the analog subsystem. The 12-bit SAR can sample at a speed of 12 megasample per second. I will explain the ideal sampling method used here in a moment. Just wait. And in addition, it features synchronous sampling, which makes it easier to time readings in the control system. Although we can read signals in parallel, we still need sequential processing to handle them. This is where the sample and hold features help us. It allows signals that are read simultaneously to be held until they are processed. Since we know the expected range of the signals being read, we can use the range checking feature to eliminate abnormal values or just detect unusual conditions and take appropriate actions. As I mentioned earlier, with the comparator and the DUC structures, the signals can be evaluated independently of the ADC process, allowing necessary actions to be taken with less than 10 nanoseconds latency. Looking at the benefits, we see the ability to read multiple signals, BOM savings with internal analog structures, no need for CPU power due to the signal connections between modules, and the capability to perform cycle-by-cycle current control is critical for the motor control. And now let's take a closer look at the idle ADC sampling feature we mentioned earlier but postponed diving into the details. In conventional ADC sampling, the sampling starts with a trigger signal and conversion happens after the sampling is complete. During this time, the peripheral is busy. Because of this, jitter can appear in the sampled signal. If you want to increase the sampling frequency, the sampling time shortens, which requires a higher input current. This higher current demands leads to the need for an external capacitor. But on the other hand, the idle ADC sampling method used in the PSOC Control C3 comes from the automotive grade AURIX platform. In this method, because sampling is continuous, the peripheral is busy only during the conversion step. As a result, the capacitor in the sampling circuit does not discharge before the next reading. This allows sampling at a high frequency without jittering on the sampled signal. Additionally, there is no need for an external capacitor. As shown by the two graphs on the screen, idle sampling provides the most accurate representation of the real signal, not just looking for the digital type, like as an analog signal reading, the real one. And we need the timer block for the motor control. Here we see a reference block diagram of the timer structure used in three-phase motor control application. Taking a look at the key features, we can clearly understand the capabilities it offers. By using three TC-PWM counters, a three-phase motor can be controlled using center-aligned or edge-aligned PWM signals with dead time. And also the other one generates the motor control period. The other counter or counters generates the motor control signals, PWM, and the last counter generates delay for ADC triggering. You can easily set your delay or latencies with these counters, and three PWMs can be activated simultaneously using overflow of PWMs or software command of trigger multiplexer, depends on your control method. And parallel sampling of three motor currents are possible with advanced and fast SAR ADC, as we mentioned. And also the last one, built-in comparator with internal tag can trigger a kill signal to PWM to switch off PWM to safe state. And with the multi-channel pattern of the PWM, synchronous updates on the output signals are possible. Here we can see a comparison between the PWM, HR PWM, with and without HR feature and without the HR feature at a switching frequency of 1.5 megahertz and a duty cycle of 50%, we can reach more than the double in resolution using HRPWM, which is 12.3 bits. In here you can see. And if we summarize the technical features which we have discussed on a single page, we can clearly see that each one brings a benefit to motor control. Like as the feature is coming from the analog side and the digital peripherals, like as the HRPVMs, and with some accelerators that create the benefits, enable high performance system to respond to real-time events and multi-motor controls for your projects. The other one, high sample rate and autonomous, it's creating another feature to using with the wide band gaps products, silicon carbides or gallium nitride switches, and precise analog processing and digital control to improve control loop accuracy and system benefits. And also, as I said, that product has the PSA L2 certified and SIL 2 compliant and Class B compliant safety libraries. That means enable secured on-site and cloud-based systems with the L2 certification and implement functionality safe solutions with the safety libraries. And I think I can catch my time, and I am switching back to Wolfgang for a Q&A session.
Yes, thank you very much, Canberg, for your two lectures we had. And we just look through the questions from the audience and pick out two or three that are of interest to everyone. Of course, all other questions from the audience will be answered by email after the Knowledge Lab in the next days. Yes, we have some questions here. The first one is, which features does PSOC C3 offer for motor control with gallium nitride?
Okay, it's a good question, and I can say PSOC Control C3 brings several important features that make it ideal for motor control with gallium nitride switches. One key advantage is it is idle ADC sampling method. As I mentioned, we have already covered this feature in detail. And another important feature is the high resolution PWM. It enables precise and high-frequency PWM generation, which is especially critical for driving gallium nitride due to their fast switching characteristic. In addition, PSOC C3 includes a rich set of peripherals that can be interconnected through internal routing. With this, we can link PWM outputs or ADC inputs and other control signals directly inside the chip and without using the core performance. So it's very powerful method to creating the gallium nitride fast loops. This flexibility lets us build high-speed control loops that run almost entirely in hardware and preserving core power and improving overall response time and efficiency. Overall, C3 offers a very capable and efficient platform for high-performance motor control with gallium nitride.
Okay, thank you. And we move to the second question. Are there different power modes for low power application development with PSOC C3?
Yes, when developing low power applications with the PSOC Control C3, there are actually several power modes available to help balance performance and energy efficiency. Specifically, there are six different low power modes, each offering unique features, varying performance levels, and different wake-up options. This allows you to tailor the power consumption based on your application needs. On top of that, there are four different active modes. It's critical one, which differ mainly in their maximum clock speeds. So depending on how much processing power you require at any given time, you can select the correct active mode to optimize both performance and power usage. Overall, this variety of modes gives you a lot of flexibility to design energy efficient system without sacrificing the necessary performance. And as I remembered, names is active sleep, deep sleep, hibernate, and sleep RAM and deep sleep off, like us. Yes.
Now we have hopefully the right motor and the right controller. What do we need to consider when designing the application? What are the trends here? Sergio Piovella from EBV Electronic takes care of this. Sergio is a field application engineer specialized in power electronics and has been at EBV for 12 years now. He's located in Munich and he is responsible for customers in Central Europe.
Thank you very much for the introduction. I'm going to go through a little bit what are the power design trends in motor control and highlighting the latest technology from Infineon concerning semiconductors which are suitable for driving motors. I will go firstly through what is the state-of-the-art silicon IGBT technology and the silicon carbide MOSFET technology from Infineon. And I will focus concerning the silicon carbide MOSFETs on the Cool SiC generation 2. And this part will cover mostly high voltage topic. And the second part, it's a little bit more on a mechanical side related to topside cooling, so which is a new trend in package. And last but not least, also as it was mentioned in the presentation from Jomberg, also about Cool GaN, which is the gallium nitride technology from Infineon. So let's move to the silicon IGBT. The latest technology is IGBT7, and as you can see, Infineon has always been ahead of the curve by introducing the first IGBT2. The planar IGBT is already from the 90s, actually beginning of the 90s, and then trench field stop, IGBT2, and then 3 and 4, which was introduced in the year 2000s. And a few years ago, and now in full production, and the latest technology available is the IGBT7 technology from Infineon, which is sort of improved trench field stop technology with this so-called pattern trench, which further reduces the losses and increases the efficiency of IGBTs. A little bit about IGBT7. What are the main characteristics? There is, of course, for motor control, it's very important that the technology is robust. So the IGBT 7 technology is defined to be up to 8 microseconds in standard operating condition of short circuit capability. There has been an increase in power density compared to previous generation, considering the same package. So is it possible to have TO247 4-pin devices which are generating 25%, or it's possible to extract 25% higher current out of a TO247 standard 3-pin device? Of course, compared to the previous generation, it reduces the losses, mainly focusing on the conduction losses, which and I'll tell you about why in a sec. Of course, the IGBT7 technology comes with its own pendant diode, which is EC7 family, which is co-packed into the discretes or into the modules available from Infineon. Improved humidity and cosmic ray ruggedness make it also reliable for the most harsh applications. And as I mentioned before, focusing on conduction losses, as this family is mainly optimized for motor drive applications and can be operated at, and it's optimized to operate below or at 5 kilovolt microseconds, which is sort of the limit in the high voltage technology for motor drives. That's how it provides up to 30% less total losses compared to the previous generations. Now let's move on to to give an overview of the CoolSiC MOSFET technology, which is the brand name of the silicon carbide technology from Infineon. Here also some interesting features or relevant features for motor drives. So silicon carbide is actually a good technology to drive motors. And Infineon specifies on certain families of devices and in modules a short circuit withstand time defined to be at least of 2 microseconds, considering again standard operating conditions. Of course, with silicon carbide, you further reduce the losses. This is a technology which has no tail currents, no losses at the end. So it makes it is very suitable for very high power density designs. In addition to that, silicon carbide lowers the switching losses compared to even the latest IGBT technologies. And since the switching behavior of silicon carbide, it's having a lower capacitance and a lower gate charge compared to IGBT7. And the intrinsic body diode, which is a full rated body diode, provides also good commutation behavior also in the hard switching application. The same can be said about silicon carbide, as we said for IGBT7, so good humidity robustness, and so same target application apply for silicon carbide. One of the biggest advantages of silicon carbide is that also the thermal behavior is far better than standard silicon. So you will realize to have basically temperature independent switching losses no matter how the temperature rises. This shows then a comparison. So is it then only silicon carbide present in industrial drives? No, because it's always a trade-off depending on the application. And for example, the switching frequency of the inverter plays a key role in defining which technology is most suited. And all in all, the IGBT7 and in general IGBTs show better static performance at nominal or high currents, whereas CoolSiC MOSFETs show a better dynamic performance, keeping the output current almost constant at the variation of the switching frequency. So these kinds of applications are very well suited for SiC to be used. So we can derive from that at increased switching frequency, CoolSiC MOSFETs are a very good choice. Now, let's focus on the state of the art of cool SiC MOSFETs from Infineon, so which is the latest generation available. It is the generation 2. And as I said, silicon carbide MOSFETs can support different application trends. And highlighted, you see two topics or two applications which are related to the topic of today. So one key application is fanless drives in industrial automation, because silicon carbide, as we said, reduces loss by reducing losses and increasing efficiency, enable inverters which can be fit into the motor itself. And the same applies for the second part, so compact integration of the inverter and the motor. This is basically two sides of the same metal. Of course, these are not the only application where silicon carbide plays an important role, but especially for motor control, there are a few improvements which make Gen 2 silicon carbide technology from Infineon really state of the art. Besides the improved chip performance, of course, over generation 1, there is an improved interconnect inside the package, which is valid for many device classes. So when we're talking discretes or low power modules, let's say, and even the high power modules, they all sort of have a variation of the patented .xt technology from Infineon, which enables a better thermal resistance. So it can extract more current out of the very small chips inside the modules and the discretes. Of course, the technology from Infineon, being a trench technology, offers the best-in-class RDS(on) to date with 8 milliohm in Gen 2 devices, which compares to a much higher 30 milliohm in G1. Furthermore, the overload operation has been increased, so that the junction temperature which can be achieved in this overload condition can reach 200 degrees. And there is also been added the avalanche robustness to the cool SiC generation 2. The maximum RDS(on) is also now specified in the datasheet. So Gen 1 did not specify this value, but now the parameter spread has been further reduced, and therefore it is possible to specify also at high temperature the maximum RDS(on) for each device, enabling you to dimension your design in the best way possible. Short circuit rating has remained, so 2 microseconds, as we said before. And what is very important for silicon carbide devices is the gate source voltage robustness. And Gen 2 can tolerate between minus 10 volt and plus 23 volt gate driving voltage, which makes it compatible with basically all the silicon carbide drivers and silicon carbide devices from competition, enabling you to design Infineon no matter what other technology from which other supplier you were using before. This gives an overview of where we stand today with the cool SiC Gen 2, which are being released between 2024 and 2025. As you can see, Infineon is the only in the market to play at a very spread amount of voltage classes, so from 400 volt to 1400 volt. And I will not go through every single device, but you should not miss any device, any package in this portfolio. And this slide also reports which packages are available in which generation in automotive and industrial qualification. I will come back to later to the many topside cooling that you see in this slide with a dedicated session later on, which is beginning now. So what is topside cooling? It's basically a power package trend, mainly on discretes, of course, on power discretes. So the idea is to combine the advantage of through-hole devices and SMD devices. So the advantage of through-hole devices, especially in TU247, is the high thermal performance. But the drawback is that it requires manual handling and it has a low pin count. Therefore, also package inductance is sometimes a limiting factor, whereas the die inside could switch much faster. On the contrary, SMD, typical D-square packs, which are very common for silicon carbide with 7 pins. This is very familiar for who has designs in silicon carbide using discretes, has a much more limited thermal performance. You probably would need an IMS substrate or a PCB with a lot of thermal vias, and the heatsink will not be directly connected to the devices. So the thermal junction the thermal resistant part, it's impacted by this. On the contrary, having SMD devices enables fully automatic handling, so it is good if you have high volume production, and high pin count, as we said, reduces inductances and increases the current which can be extracted out of the package. So topside cooling, now we come to the innovation, is basically combining the advantages of both. So you will gain the high thermal performance of a through-hole device, but you will keep the automatic handling and the high pin count. The difference is that instead of having to heat dissipate through the bottom, the package is made so that you can connect a heatsink to the top, and you can also, given the tight tolerances of the package, connect many devices on the same board, and eventually you use a single heatsink. This translates in what we can see here. So a much simpler system assembly when you can put SMD topside cooling devices in your design. And these are real life examples where you basically reduce the amount of connectors and you simplify the PCB. And in the end, you bring a lot of advantages at system level. Whereas at device and component level, there is not a huge difference in price between SMD bottom side cooling and SMD top side cooling. And with the increase of diffusion of these top side cooling devices, I am sure that the prices will also align with SMD bottom side cooling. Here is a little bit of a more mechanical slide, which shows how, for example, you could assemble topside cooling devices. In this case, Infineon started with a gap filler material and topped by an isolation foil, and then on a liquid cooling application. Whereas on the lower part, the PCB is a standard PCB. Here have been tested different thicknesses on the right, you see in the graph, and measured the thermal resistance. And we see that with different performance of thermal gap filler and isolation foil, you can reach very significant differences, and in the order of magnitude of 2 Kelvin per watt, you basically reach what is comparable to a TO247 device connected to a heatsink, but with the advantages of SMD. So as I showed before, Gen 2 and Gen 1, but not only silicon carbide is available in topside cooling. There are basically many devices and many product families which are available from Infineon in topside cooling variants. So the one that you see, which is having a slight bigger footprint, it's the so-called QD pack, whereas the smaller footprint is the TOLT device. And these devices, so TOLT is limited to 650 volt due to creepage and clearance distances, and with QD pack you could reach 1200 volts. And not only, there are variants of QD pack which are available today, which are basically combining two switches in one package, or a switch and a diode to compose basically the simplest cells in AC-DC or DC-DC conversions topologies. So not only silicon carbide, but also IGBTs will be available, and they will be available during the course of the year. Now for my last part, I would like to introduce CoolGaN, which is the gallium nitride technology from Infineon. And these are the different product families that Infineon will launch over the course of the coming months, quarters, and years. So from left to right, you see an increase in complexity and integration of the device around the gallium nitride transistor. And let me go quickly to talk about the advantages of CoolGaN transistor and combined with field-oriented control in motor drives. So CoolGaN, as in comparison to silicon, whether it is low voltage or high voltage, has a much lower specific on resistance, a much lower QoSS, and a linear output capacitance. The QG is also lower, and there is basically virtually no reverse recovery because we have no diode in a GaN transistor. Additionally, GaN is available in low inductance packages traditionally, which further enables increase in switching frequency. So when you combine it with field-oriented control, you aim at reducing switching losses. You can target higher switching frequency. You will result in cleaner switching waveforms. And last but not least, you can also reduce the dead times, which are then another element which impacts the overall efficiency. So the aim of GaN, as we see today in the market, the trend is to design heatsinkless designs. So increase the amount of power which you can aim at by without having to use an heatsink. In general, also switching at a high switching frequency, you reduce the current ripple, so the efficiency of the overall system increases, and the torque ripple, so you will also reduce the damage on the wear on the motor itself. Of course, with a higher switching frequency, you have a higher control loop bandwidth, and you can increase the motor control dynamics. This is why applications such as drones or servo drives in 48 volt applications are especially a trending topic for gallium nitride at the moment. So let's have a look in detail about the application. So medium voltage GaN, medium voltage we consider anything below 400 volt, and high voltage anything above. So you can see e-mobility, robotics, and servo plus home appliances. And a power range which can reach up to 10 kilowatt because we're talking about low voltage here. Whereas high voltage GaN, we have compressors, drums, pumps, which can be found in many markets, not only industrial, but also consumer markets. But here the power would be more limited, like maximum 2 kilowatt. Also, again, the target in this kind of application is to remove the heatsink and increase the efficiency. And removing the heatsink for this cost-effective, cost-driven markets, it's a key advantage. There is already today available a lot of hardware which you can test on. Here are, for example, 3 demo boards which have been released over the course of the last year and the beginning of this year. So you can already go to Infineon.com or contact EBV if you would like to acquire one of these boards. These are all reference designs targeted at motor control with different power level. And as I said, this have all been tested to 100 kilohertz and more. So you can really try to achieve to exploit the maximum out of GaN, and you will also find design files which can help you define the layout of your gallium nitride inverter. What about high voltage CoolGaN transistors? So I mentioned there the power is not that high compared to low voltage, but here again the goal is to remove the heatsink. So what GaN technology and the GaN devices available from Infineon can aim at with their packages that you see in the middle, which are some of them already released, some of them are upcoming, to push a little bit towards the kilowatt and 2 kilowatt range, the heatsinkless design. There is a lot of material which can be provided. So if you are thinking about a new design which is in this range, please get in touch with us. Let's see a comparison. So it's not only just about words, but in general, we can see a comparison with 600 volt IGBTs and the latest CoolGaN Gen 5 products. So from the breakdown voltage, but also from the forward voltage of the diode compared to a reverse conducting IGBT typically used in white good application, you see how the lower conduction losses you see how conduction losses are much lower, and of course the switching losses are even in comparison lower, which enables a continuous hard commutation because you don't have QRR, and as we said, the capacitance is linear, the output capacitance. And in light load condition, you also have a smaller input capacitance, which reduces in the end the gate driving losses. So all of this contributes to reduce the losses, the total losses of the system. And here we see a calculation using a calorimetric method and simulation for the IGBT part. And we see that with gallium nitride device, you can even reach up to 70% loss reduction compared to an IGBT design, and especially at 50% load and 100% load is where this huge difference comes into play. So that's it for my presentation. I hope that I gave a short brief, however brief, but a good introduction to the different technologies for motor drives which are available at Infineon. And yeah, back to you, Roland.
Yes, thank you very much, Sergio. We have picked out some questions, and I will ask the first one from the audience. It's about CoolSiC Gen 2. I see you are mentioning only discretes. We are using EC1B modules from Infineon with Gen 1. Is there a plan to introduce Gen 2 in the same form factor?
Good question. Yeah, I did not mention the modules in Gen 2 because they are upcoming. So yes, there gonna be there is a plan to introduce Gen 2 also in EZ1B, and if you attended the PCIM, you might have come across. And there is also a plan to improve the easy modules, but keeping the same form factor. So also this module can perform better together with Gen 2 products. So if you are looking for more information on that, you can get in touch with us or Infineon directly if you're supported by Infineon, but we are happy to support.
Okay, thank you. Second question, I would like to start a new motor control project using GaN. Where should I start?
I showed some of the eval boards which are available, and this you can buy already off the shelf. So this low voltage GaN or medium voltage GaN boards can consider a good starting point. There is also these are power stages, so you will also get compatible motor controller. So you can also build a complete system, or you can attach your controller to test with your controller the gallium nitride power stages. For high voltage, I think something is in the works. I'm not sure that is publicly available, but there is a lot of material, and there are a lot of measurements performed with the initial generation 5 devices, but also upcoming devices which offer also integration. So again, ask EBV and we can support.
Okay, thank you. And third and last question with maybe a short answer. You have not shown any info regarding reliability of GaN, and the applications are not considered safety relevant. Is there an issue on GaN reliability?
No, very good question again. So actually, Infineon plans to qualify gallium nitride for automotive use, and there is a lot of material already available again, upon request concerning quality, the reliability, lifetime estimation, and stability requirements, which Infineon takes into consideration for GaN. So these are all based on accelerated tests and simulation, and again, they are available.